Okay, so now I want to talk about what's called star distributions in the analytic sense. So recall how abstraction allows us to, or it encodes the information we have about our probability measures using moments only, right? So we have the algebra, we have the powers of elements, phi of a power of an element or of a product of elements, whatever, captures moment or joint moments, but what about the distribution in the kind of analytic sense, the usual sense of, a probability density function and so forth? So that's where the star distribution in the analytic sense comes in. The point is that we would want to always work with moments because we want to work in this abstraction, algebraic abstraction, which will also kind of uncover or reveals to us the fact that there is a nice combinatorial structure underlying a free probability and also the standard probability. But at some point, sometimes we would want to infer information about the probability measure itself. Forget about the fact that I'll need to define precisely what a probability measure is. It may not be what you think, but still, I mean, how can you do that? So there are ways of doing that. We'll see the Stieltjes transform and so forth, but for now, let me just introduce the basic concept, okay? And okay, so this is a definition and theorem combined, so that's the theorem here. So say you have a star probability space, right? You have A, you have phi, and generally things are non-commutative there. So let's take a normal element. You will see in a second why we need A to be normal, but recall that a normal element is an element that commutes with its conjugate, right? So the thing is this: if there is a probability measure, a nice probability measure that underlies the moments that we encode. So for what I'm saying is that if there is a measure mu, and this symbol d mu z, just think of it as you usually think of it for now. It's just, mu z dz. Think of it as a shorthand for mu z dz, even though it's not generally true. But, it's best to think of it like that. And for now, and mu of z is just the probability density function. Okay, so if there is a measure mu under which any polynomial in z and z bar, so z to the k, z bar to the l, so the integral, so the moment of that function, right, or a variable, is encoded by our phi in the right way, namely, of course, phi of a to the k, a star to the l. If that happens, if there is a probability measure like that, which is nice, and we'll talk about nice in a second, then that measure is unique, essentially, but unique. There are measure theoretic stuff that you need to talk about, and we'll talk about, but it's essentially unique. And because it's unique, it's called the star distribution of A in the analytic sense. Analytic because you have this analytic description of the algebraic information that you have on that side. Okay? So that's the star distribution of the analytic sense. If there is like a reason, an analytic reason, analytic measure, like plain old measure that encodes the moments that which are the only thing we are encoding within the algebraic structure, then it's unique. Now, usually it does exist in our settings. So the if is a kind of well-behaved star probability space, and elements in them have such a measure. And by nice, I mean compactly supported. So the best way to think of compactly supported is just as its support is bounded and closed. So it's just essentially composed of a union of, closed intervals in the reals. In C, it's a bit more complicated, but generally speaking, a set is closed under the kind of topology we are using here if every accumulation point is in the set. Namely, if you take a Cauchy sequence, namely a sequence that converges to a point, then that point must also be in the set, not outside of the set. right? So an open interval is an example of something that's not closed, because you can take a Cauchy sequence and a sequence of elements that get closer and closer to each other, but the limit point, which certainly exists as an element of R, doesn't exist inside the open interval, right? So don't worry too much about it, but that's that. And note also that we really had to work with a normal element, because there is no way something like that can happen in general for a non-normal element, because for normal elements, the only moments we have to consider are a to the k, a star to the l, because if you have an a star a, you can always shift things around, right? Because a star equals a star a. And on that side, like in the analytics, on the analytic side of the equation, z and z bar will commute, because these are just complex valued numbers. So you on the left-hand side, the analytic side, cannot support non-commutativity, right? So even if the algebra A is non-commutative, once you have an element which is normal, then restricted to that element, namely looking at the algebra generated by it and its conjugate and one, once you look at that, you do get a commutative space, right? And then there is a hope that there is a measure that underlies the information encoded in the moments. Okay, and if you are curious about why it's unique, then don't worry too much. But really, what you see here in this equation is that all polynomials are determined by phi, and using the Stone-Weierstrass theorem, you should be a bit careful and so forth. You can show that all continuous functions can be approximated by polynomials in compactly supported domains. And from there, you can reach to the conclusion that the measure must be unique. But never mind that. We are not really going to use this theorem anyhow. It just serves as an example, mostly. Usually, we are just going to find mu, and that's it. So to give an example, let's consider a star distribution of self-adjoint element, right? A equals a conjugate, which is a particular case of a normal element. And for matrices, for example, we know that, right, if you have a self-adjoint element, then its spectrum is real, a self-adjoint matrix, like a symmetric matrix. When its spectrum is real, that's how we started the introductory talk. So let's prove that in more generality for a self-adjoint element in a star distribution, star probability distribution. So let's see why the star distribution of a self-adjoint element is real. So right, here's the setting. You have a star probability space. Sorry, I said distribution, I meant space. And you have a self-adjoint element. And let's assume that this has a star distribution mu. As I said, not every element has a star distribution, but let's assume that. And I want to show that the support of that distribution is real. So what I'm going to do is look at this integral, and I'm going to show it 0. Right, so I'm integrating z minus z bar modulus square against the measure. I'm going to show it 0. And maybe let's start there. So why is it 0? Well, z minus z bar squared is just z minus z bar times its conjugate. But its conjugate is z bar minus z bar bar, which is z. So that's what you see here. Then you just open it up, and you see that of course, the integral is linear, so you see that you get twice the integral of z bar according to the measure, which is encoded by this value of phi. And then similarly, you get minus phi of a squared and minus phi of a star squared. But a equals a star, so this is 0. You have two of the same thing, you subtract twice here. So this means that the integral is 0, but this function that takes z to z minus z bar modulus squared is continuous and non-negative. And so once you have an integral over a continuous and non-negative function, which is 0, it means, and again, measure theoretic aspects aside, that's the asterisk here, it means that the value itself is 0 on the support of mu. Okay. But if this function that we integrate over is 0, then because everything here is faithful, right? It means that z minus z bar is 0 on the support, which means that z equals z bar on the support, which means the support is real valued. So that's that. In the recitations, Gal will show you other examples, very nice examples of the star distributions in the analytic sense of different elements. Good. So let's see. Oh, so I think I didn't do that in class. I knew I missed something in class, but let me just do it here anyhow. So here is another example. So now let's take A to be a normal matrix, right? So we are looking at the star probability space of D by D complex value matrices. And we take a normal matrix. And let's say it's a normal matrix, meaning it has a full kind of basis of orthonormal eigenvectors, and denote the eigenvalues by lambda 1 up to lambda d. Then, what's the measure that corresponds, if it exists, that corresponds to this element? Well, the phi that we took in that example is the normalized trace, right? So the normalized trace of a general element, a to the k, a star to the l, right? A is normal, so that's a general element. Is it's the normalized trace of this matrix, which is exactly this thing. And what we want is to have a measure for which this equality holds, right? We want a measure that explains the moments. And if you think about it, but don't think about it too much, then the measure is this thing. So it's this called it's a sum or an average of the Dirac measure at the different points. So really, the Dirac measure, or something called the Dirac function, even though it's not a function, is in a sense a measure that assigns zero value outside. So delta of p is this function that assigns zero value outside of p, and some value, you want to say 1, you want to say infinity value at p, such that integrating with respect to this measure is the same as evaluating the function that you're integrating at p. Okay, so something like, if I'm using a variable here, right, integrating, sorry, this is p. So integrating with respect to this measure, any function, any integrable function, is the same as evaluating at p. So everything is zeroed out by the measure outside of p, and inside of p you have enough probability mass that exactly corresponds to evaluating there. Turns out that it's in order to really define that thing, the Dirac measure, you need to know a little bit about measure theory, and you need to work with Lebesgue integrals and not Riemann integrals. And we'll do all that because I don't want it to be like a weird aspect that you don't understand, even though it's not like the main thing in the course. It's just, but it's something that will always be there, so you need to feel comfortable with it. So at least for now, just know that there is a measure, which is the measure that assigns, that is the kind of the average of Dirac measures corresponding to the eigenvalues. Okay? And you can ignore that; it's not so interesting. I just explained why this equality holds for a particular case, but it holds in general anyhow. Good. So now there is a bit of philosophy here, which I hope I'll be able to convey well. So if think of, let's revisit this notion of freeness, this kind of weird notion of freeness. So say you have now we're in a better position to talk about what freeness is. So say you have two matrices, A and B, like we had before, and that they are free, whatever sense, whatever it means. Then, right, recall that A and B are just deterministic matrices, right? But To each of them, we associate a distribution, which is the uniform distribution over the corresponding eigenvalues. And the distributions are independent in the sense that when I sample an eigenvalue from here, I use fresh coins, when I do it here. But even if I do that, it doesn't tell me how does the spectrum, like the eigenvalues of the sum behaves, right? Because it depends on the eigenvectors, which are not present in the eigenvalues, right? The eigenvalues, the distribution over the eigenvalues is not the thing. It's not that there is there are correlations between the way you sample eigenvalues of A and B. It's that the eigenvectors of A and B, which are is additional information over the eigenvalues, right? That's the problem, right? So in a sense, freeness, and we kind of implemented freeness by looking at something like that, by rotating B. So in a sense, freeness is a way of freeing the distribution. So in the example of matrices, where I'm right now, right? So freeness is the thing that is something that happens not in the distribution themselves, but actually in something that underlies them, the eigenvectors. So I'm just trying to, there is this point of confusion that says, well, if A and B are deterministic, then first of all, already to begin with, it's kind of weird that you think of distributions of these matrices. It sounds a bit weird that I associate a distribution of sampling and eigenvalue. But even if I do that, it's not that they have correlations in the way I choose eigenvalues of A, eigenvalues of B, which is the problem. It's the structure of A and B, the non-commutative structure, which is determined by the eigenvectors, not the eigenvalues, right? So freeness in this instance is manifests itself as a rotation or something, right? So that's what I try to write here. So it's not enough to. It's not that mu and A and mu sub A and mu sub B, the distributions of A and B, it's not enough that they will be independent in order to say something about the spectrum of the sum. You need a structure that respects in this case, the underlying eigenvector structure, right? So it's not something that's present in the distributions alone. Yeah, I'm not sure if it's helpful or not, but if at some point you get confused about how could it be the case that the independence of sampling eigenvalues is not enough, and that's a good point to look at again. Okay. Okay, so this is the example that Gal did in the. Okay, let me just do it quickly. It's very easy. So here is one last example, and actually a very important notion also. So say you have a star probability space. An element is going to be called unitary, Haar unitary. It's going to, of course, be related to Haar unitary in the sense that I was talking about matrices. If it's first of all unitary, namely you have this property, but all moments except for the zero moment, phi of 1, phi of u to the 0 is 1, because phi is unital, all moments vanish, which is what will happen if you take a unitary matrix and take its power and look at the moments. It sounds weird that there is such an element up until you remember the fact that for unitary, it's exactly what happens. So that's the corresponding star distribution here. I mean, it's a normal element. There could be a star distribution there. So that distribution, if you think about it, I mean, it's not maybe easy to come up with, but it's easy to verify that it's the uniform distribution over the uniform, over the, cycle, like I forgot the name, this thing, anyhow. מעגל היחידה, anyhow. So once I give you that, it's kind of easy to verify, right? Because what do you need to check? You need to look at phi of UK U star L to the L. That's a general element. And because we are working with unitary matrices, unitary elements, U star is just U inverse. So you get this thing. And then because of our definition of a Haar unitary, you see that when k is L, you get a 1. When k, because it's 1, and it's a unital phi. And when k is not equal to L, you get a 0, right? Good. So now we just need to check that that's the same, that happens also with our choice of measure, right? So, oh, there should be a mu here. Yeah. Okay. So indeed, if you take the measure that we defined and integrate z to the k z bar to the L, well, moving to polar coordinates, you looking at the integral from 0 to 2 pi of this thing, right? I'm just plugging z instead of z, I'm plugging e to the I, e to the I. Well, yeah, that's it. E to the I to e to the it, sorry, and then I have the dt over 2 pi because of this is a uniform measure of the unit circle, unit disk. And this thing is it's easy to check that when k is L, it's obviously 1, and when k is not equal to L, then you can easily check that this is 0. Okay, so this kind of maybe weirdly looking algebraic definition of Haar unitary, so the moments are all 0 except for 1, the measure that explains it is the uniform distribution over the unit disk, unit circle. Okay, so I think that's enough for today. Next time we are going to do measure theory 101. I'm going to explain things about measures that you'll need to get, and also a bit of complex analysis, especially analytic continuation, but we also have to feel comfortable with working with branch cuts and stuff like that. So it's a basic stuff, but we should see it once.